Everyone. Today I will present our paper, Peripheral Teleportation, a rest frame designed to mitigate cybersickness during virtual locomotion. Traveling virtually using a controller or virtual locomotion is the primary cause of cybersickness in VR, which is induced by visually perceived motion. The peripheral vision plays an important role in motion perception because it is more sensitive to motion. The primary focus of software-based technique is to reduce optical flow in the periphery. Currently, the field of view restrictor is the most widely used cybersickness mitigation technique. An FOV restrictor eliminates peripheral optical flow by turning the outer ring of the field of view black. However, reduced field of view comes at a cost because wider field of view is desired. Larger field of view can contribute to better user experience, enhance depth perception, and provide better performance for searching tasks. Manufacturers of VR headsets are developing products with wider field of views. There are many other software-based techniques that address the drawback of symmetrical black field of view restrictors. Among them, there is the rest frame technique, which allows visual content in the periphery. The downside of the current rest frame design is it still partially blocks the virtual environment, and previous results were inconclusive on the effectiveness of a dynamic rest frame. Despite this, ecological psychologists predicted that Earth-referent rest frames are the most effective cybersickness mitigation technique. However, this hypothesis has never been explored before, and there has been no previous work attempting to design a rest frame without blocking the virtual environment. Unlike previous rest frame implementations, we created a rest frame in the periphery using content from the virtual environment. We created two extra sets of cameras attached to stationary camera rigs. The local transform of these cameras are the same as the HMDs, which means their motion is only affected by the user's physical movement. As a result, the output of each rest frame camera serves as a rest frame. The periphery is blended by the output of these two cameras based on the small t, or the time lapse since last teleportation, using this given equation. The positions of the rest frame cameras are teleported once every capital T seconds. Here's an example. We set the teleportation interval capital T to 1 second after internal pilot testing. When the user starts to move, camera RF1 is placed at the same position and orientation as the HMD. RF0's position is predicted based on the velocity of virtual locomotion and capital T. Because small t is 0, the interpolant is 0. Our rest frame 0 is invisible. So the blended image is exactly the same as the HMD's view. But after 0.3 seconds, the interpolant becomes 0.3. RF0's image is starting to show up in the periphery. And after 0.7 seconds, RF0 is becoming dominant. And after 1 second, the interpolant is 1, and RF1 is invisible. Theoretically, if the user does not deviate from the predicted path, the blended image should be the same as the HMD's view. Since RF1 is invisible, it is a good time to teleport it. And now the whole loop starts again from the beginning. Here's a video showing how it works for translation. On the left side, you can see how rest frame cameras are teleported consecutively. And on the right side, you can see how the view transits from one rest frame camera to the other. For turning, it works in a similar way by replacing teleportation with snap turns. We used an asymmetrical side restrictor design based on a previous paper. We conducted a between-subject study with 90 participants to evaluate the effect of peripheral teleportation on cybersickness. Three conditions were included in this study: an empty control condition, peripheral teleportation, and a black field of view restrictor, which occupies the same area as peripheral teleportation. Participants' task was to navigate a virtual city while standing. There are 10 tries in total. Each lasts about 2 minutes and a half. Participants rated their discomfort score at the end of each trial. If they gave a rate of 10 or reported severe discomfort, the navigation task was terminated immediately. We measured participants' cybersickness level with the SSQ and discomfort scores. Task duration is also included as an objective measure of cybersickness. We asked participants to terminate the task when they feel severe discomfort. The longer they stay immersed means they feel less discomfort. We also measure the perceived visibility through a 7-point Likert scale and use a sense of presence. We hypothesized that peripheral teleportation and field of view restrictor will have significant effects on cybersickness, which are reflected by SSQ scores, discomfort scores, and task duration. We also hypothesized that both peripheral teleportation and control will provide higher visibility and sense of presence. Here are the results. First, the median immersion time in the peripheral teleportation condition exceeded 20 minutes, significantly longer than the 10 minutes observed in the black restrictor condition and the 6 minutes in the control condition. The SSQ scores were not significantly different, but this can be explained by the large difference in immersion time between the conditions. Our study protocol required participants to stop using VR when they're sick. The similarity in SSQ scores across the conditions suggests that cybersickness severity was fairly consistent when participants reached the stop criterion. And the large effect size of task duration supports our hypothesis. Similarly, for average and relative discomfort scores, we observed similar effects between the peripheral teleportation and control. This result confirms the effectiveness of peripheral teleportation. Originally, we did not expect to see significant differences between the two cybersickness mitigation methods. However, participants in the peripheral teleportation condition also reported significantly lower discomfort compared to the field of view restrictor. We did not find any significant differences in visibility and the sense of presence. Our results are of particular interest to the research field for the following reasons. First, we confirmed the effectiveness of a dynamic rest frame despite previous papers considering it as a weaker technique. Our results suggest that the lack of significant findings in prior studies should not be overgeneralized to all rest frame techniques. Second, our study is the first direct comparison between a field of view restrictor and an Earth reference rest frame with a consistent occluded area. Finally, peripheral teleportation is the first software-based cybersickness mitigation technique that has significantly enhanced user comfort over the commonly used field of view restrictor. Our results open new directions for cybersickness research, especially for the rest frame technique that remain underexplored. As with any experiment, there are limitations of this work that should be acknowledged. The design of peripheral teleportation can still be improved. Our current implementation may introduce discontinuities in the visual content. The visual artifact is similar to screen tearing at the restrictor mask boundary. A gaze contingent rest frame design may help solve this problem. We also selected parameters for peripheral effect based on informal testing, which leaves space for optimization. And finally, the effects of peripheral teleportation can result from factors other than optical flow, such as attention shifting and luminance change. These factors should be examined separately to fully understand the mechanism of this technique. In conclusion, the peripheral teleportation we proposed it produced significant innovations on cybersickness mitigation. The peripheral teleportation technique is the first cybersickness mitigation technique to enhance user comfort beyond industry standards. VR practitioners can add this technique to the cybersickness mitigation toolset. Thank you for listening.